Module 4 on solution of discrete algebraic systems. In this module, we would focus on the solution of discrete algebraic system of equations which we obtained earlier using finite differences. We would get fairly similar systems if we use finite element or finite volume technique for spatial discretization. So, we would have a brief look at the features of these discrete algebraic systems, and we will discuss in brief which solution methods are best suited for these systems, specifically in the context of CFD applications. And as we know that our Navier-Stokes equations, they represent a system of coupled nonlinear equations. So, we will have a brief look at solution methods for nonlinear systems. We might also get nonlinear systems arising from finite difference or finite element discretization of nonlinear heat conduction problems. So, that is why we will first have a brief look at the solution methods of nonlinear system, and then solution of any nonlinear system involves solution of a set of linear algebraic equations as the part of the iterative scheme. So, we will discuss in bit more detail direct as well as iterative methods for solution of linear systems. We will have a look at what we call basic iterative methods for linear systems like our Jacobi or Gauss-Seidel iterative schemes, and we will see some accelerated schemes based on Krylov subspace acceleration and multigrid techniques. So, in today's lecture we are going to focus on the first two topics in this module. While discussing the schemes, we will restrict ourselves to the ones which are most commonly used in CFD analysis. Otherwise, you can pick up any book on solution of linear systems. There are plenty of schemes available. Similarly, there are a number of schemes available for solution of nonlinear algebraic equations. So, we are not going to discuss each one in detail, otherwise each one would require a separate course for itself. So, we would focus very briefly on the schemes which are pertinent to a CFD application. So, in today's lecture is a bit more general. We will have a look at the general features of or generic features of discrete algebraic systems which we obtain in CFD applications, and thereafter we would focus on, very briefly we will touch upon the methods for nonlinear systems. In particular, we will derive or discuss what we call sequential iteration, it is also referred to as Picard iteration, and Newton-Raphson method. Okay, now let us have a look at our basic features of discrete algebraic systems which we get in CFD analysis. So, remember our Navier-Stokes equations, they themselves represent a set of three coupled nonlinear partial differential equations, and they have to be solved in conjunction with the continuity equation and, for compressible flows, energy equation. So, for compressible flows, say for instance, we will be dealing with a system of 5 coupled nonlinear equations, and their discretization using finite differences, finite element or finite volume techniques will give us a set of coupled nonlinear system of equations which must be solved to obtain the numerical solution for velocity field, pressure and density field. Now, there are two approaches which can be utilized, that we can combine all the nonlinear systems which we have obtained from discretization of, let us say, continuity equation, 3 momentum equations and our energy equations, and thereby obtain a big system of nonlinear equations and solve the system simultaneously to get our density, velocity field and temperature field. But this approach is used rather uncommonly in CFD. What is more common is what is referred to as sequential iteration, that is, we would start off with that guessed value of the velocity, pressure and temperature field and solve each equation in turn, that is let us say x momentum equation, y momentum equation, z momentum equation iteratively, and then update the remaining components. So, we will solve each equation in turn one by one, that is why we call it as sequential iteration, and this is the preferred approach in CFD. The reasons would be become clear when we look today at the solution methods for nonlinear system, that why we normally prefer a sequential iteration approach in CFD applications. And if let's also be aware of that the system of equations which we get, they are usually sparse. This sparsity comes in because of limited number of connections which each grid point has with its neighboring nodes. So if we have for instance, we are dealing with a simpler problem of heat conduction, if the problem is linear, then we get a sparse linear system. If it is non-linear, then again this sparsity pattern is anywhere there. So whatever solution techniques which we utilize, it should support or it should make use of this sparsity feature, both in the storage of the entries of the matrix and of linear system or linearized systems, as well as in the solution process. So our choice must be based on the basic nature of discrete algebraic systems which I have just discussed. Now let us have a very brief look at method for nonlinear systems. We are going to begin with a slightly shocking comment from Press et al. In their book on numerical recipes, and the comment observation says that there are no good general methods for solving system of more than one nonlinear equation. If we had a single nonlinear equation, there are general methods which can guarantee a converged solution or a set of roots which we can definitely obtain for that particular equation. But the moment we are dealing with more than one equation, and that is what we will have in CFD analysis, we will have not just one, we will have system of the order of the number of unknowns would be in millions or billions. So we will have a system of millions or billions of nonlinear equations which ought to be solved. And this observation says that there is no general method available which can guarantee a converged solution for us. But nevertheless we have got to live with it. There are certain redeeming features of the physics which helps us to solve our Navier-Stokes equations in CFD. So we do not have to worry too much about this comment, but at the same time we should not spend too much of time on searching for a general method which, or a black box, which we can use for solving all our problems in CFD. So please be aware of it, let us not waste our energy on that. Now let us have a list of few popular techniques for nonlinear systems. They are also used for single nonlinear equation as well. We will discuss today what we call sequential or pickard iteration. This way the first or the most basic iteration scheme suggested for the solution of nonlinear problems. So we will have a look at the form of the equation for this method for a single equation, and then we are going to generalize it for a system of equations. We would say its few variants as well. The Newton-Raphson method is a celebrated method which is attributed to Newton, which is based on our Taylor series expansion. So we will also have a look at this particular method. We are going to derive the required formulae, and we will write its algorithm and pseudocode which you would be asked to translate into an appropriate program using C, C++ or Fortran, whichever may the language of your choice be. Okay, in the next category we have got what we call Newton type methods. These are popularly referred to as globally convergent method. There is a specific reason why we call them as these methods as globally convergent. Sequential iteration is also called globally convergent method because we can start off from any arbitrary initial guess, and theoretically this method says that we should be able to obtain our converged solution. Newton-Raphson methods, on the other hand, they do not give any such guarantee. Newton-Raphson method converges very fast, but only if our initial guess is close to the final solution. So that's why an attempt is made to combine the features of both the sequential iteration type of globally convergent schemes and Newton-Raphson method to what we call globally convergent Newton methods. One popular scheme for solution of single nonlinear equations, what is called second method. This can also be generalized for multidimensional problems, that is for a system of nonlinear equations. Okay. So, multidimensional second method, one particular method is what's called Broyden's method. So, we are not going to have a detailed look at any of these methods in today's lecture. If you are very keen on looking at these methods, you can find all of these methods detailed in the book by Press et al., that is Numerical Recipes in C, Fortran or C++. There are 3 or 4 such variants of this book, but basic title is Numerical Recipes. You can also find these methods in your numerical analysis. Okay, now let us first focus on our sequential iteration or peaked iteration. It guarantees converged solutions starting from an arbitrary initial guess, but the rate of convergence is often very slow. Or let us derive this scheme. How does it work? Sequential iteration. So, first have a look at this scheme for a single equation. So, let our nonlinear equation in x be f of x is equal to 0. We should try and rearrange it. So, rearrange, let us call this equation as 1. So, rearrange equation 1 as x is equal to g of x. Okay. There are various possible ways in which this arrangement could be obtained. If f(x) is too complicated, the simplest thing would be, let us add x on both the sides. So, we get x is equal to x plus f(x), and that x plus f(x) becomes our function gx. Now, our iterative process or iteration scheme let us say our initial guess is x subscript 0. So, starting from this initial guess, we would now iterate that is, we are going to now compute a sequence of numbers x of k plus 1, x of k plus 1, this would be obtained simply by computing the function g of x at k. So, x k plus 1, this we call as our new iterate. Continue this convergence process till continue till converged solution obtained. Normally for the convergence, so now this is one big loop. If you write a program, this is how it would look like. K is equal to 1, 2, 3 and so on. We will continue till we achieve the convergence. Normally we will look at the difference between 2 and we will say convergence has been achieved if the difference between 2 iterates is less than a small specified value. So, you can choose your convergence criteria. It could be based on absolute value or it could be based on a relative magnitude. So, that is your choice. there are some observations. Let's quantify these ones here. So, convergence criteria, can be based on that magnitude of xk magnitude of x of k plus 1 minus xk being less than epsilon. So, this is one possible criteria, and the second possible thing would be that we instead take a relative basis, that is xk plus 1 minus xk is absolute value divided by the absolute value of our initial guess. This is less than some specified tolerance. So, you can use either of these. Some people also take a third criteria, which is based on what we call the residual. So, third criteria could be, let's define that R k plus 1 is equal to f of x k plus 1. So, if x k plus 1 were a exact solution of system equations 1, then of course this residual would become 0. So, magnitude of this residual R k plus 1, that also gives us a measure of the convergence. So, if this is less than some other tolerance, okay, a very small number, we can say that our solution has converged. Now, the magnitude of the tolerance, that would depend on our application as well as this tolerances would depend on first thing is accuracy of the numerical computations and this is governed by what we call the precision of floating point computations. And the second one would be more of practical nature, that how close we want our converged solution to be to our exact solution. So, required closeness of x k plus 1 to exact solution. There would be certain applications where we may not like to have very accurate solution, even an approximate one will do our job. So, in that case we do not have to waste too much of our time. So, we can have what we call a broader tolerance or a looser tolerance, and if you want a very accurate solution, then of course we have to put what we call a very tight tolerance. Now, but remember that tolerance is intrinsically linked to the accuracy precision which we are going to use for floating point. If you have used single precision and if you prescribe a tolerance of 10 to the power let us say minus 10, that is meaningless. So, if you want a tolerance of the order of 10 to the power minus 10, we have to perform our computations in double precision arithmetic. And in fact, I would recommend that if you are writing your own code, whether it is in Fortran or C or C++, please always choose double precision arithmetic for our computations. Now, this was for a single equation. We want to generalize it to system equations. So, sequential iteration for a system of equations. Now, this generalization would again we will follow the same step. So, whichever systems are, so let our nonlinear system B. Let us use capital later to reinforce the fact that you are now dealing with not a single equation, we are dealing with a system of equations, and use this vector symbol. So, x is not a single unknown, it is a number of unknowns combined together, so it is a vector. So, f x is equal to 0. This is our non-linear system. Let us call this as equation 4. Now, similar to the way we did it for a linear for a single system, now let us rearrange it, or rather what we call recast equation 4 as x is equal to g of x. So, now the algorithm takes fairly simple form, very similar to the way we had written earlier. So, our iterative algorithm start from an initial guess x0 obtain what we call improved approximations by x k plus 1 g of x k plus 1, k is equal to 1, 2, 3 and so on. So, this is a simple iterative scheme. There are few variants for system of equations. So, variants of sequential iteration, what we can do is instead of writing our system of equations such x is equal to gx, so let us write or let us recast 4 as ax, where now a would be typically a matrix. So, let me put the square brackets to denote that fact. Ax into x is equal to bx. Now, obtaining this form in fact is a lot easier when we are working with a discretization scheme, because that is way we had obtained our generic equation. But remember, our equation was obtained in terms of these coefficients AP, AW, AE and so on for finite difference discretization. So, this is a natural form, this is a more natural form of nonlinear equations which we would get while discretizing our PDE or partial differential equation using finite difference of finite volume or finite element method. So, this could be our starting point. And now, what we would do is our iteration scheme would be, let us say starting with the initial guess x0, obtain the improved approximations by the iterative process given as solve A of xk, that is form this matrix A using our earlier approximation xk plus 1 B of xk. So, this is a linear system. So, solve this linear system where k can range from, let us say, 1 to so on till convergence. And once again, for convergence we can check for in two ways. One way would be based on the magnitude of the residual vector f x. So, the convergence criteria could be based on the residual of f x vector, that is, let us say, take magnitude of that vector, or the difference between two approximations x k plus 1 minus x k, get the magnitude of that vector. So, this is our simple iterative scheme, which is a slight modification of our usual sequential iteration. There is yet another way possible. We can make slight modification to this scheme and that modification is based on the choice of xk plus 1 in the evaluation of terms A, that is matrix A, and the right hand side vector V. So, let us call it as variant 1, or variant 2 could be that we would solve linear system A x0 for a vector, let us call it as x star equal to b x0. Okay, so we this instead of starting from x0, now let us obtain a bit more accurate approximation for our initial guess, and then they at each iteration solve the linear system A at x k bar. Now, this x k bar is different from our previous approximation, and we will see how to define this into x of k plus 1 is equal to b of x k bar. K is equal to 1, 2 and so on, where this xk bar, this is defined as gamma times xk plus 1 minus gamma times x of k minus 1. Now, here this parameter gamma which we have introduced to provide us a weighting. Gamma is a number between 0 and 1. Okay. So, this xk bar is not equal to xk bar, but in fact it also contains some effect of the iterate previous to that. So, hopefully this gives us a more stable iteration process. So, these sequential iteration schemes, they might look very simple, but they work fairly well. Only thing is they require large number of iterations, okay. And these guarantee, our sequential iteration process guarantees converged solutions starting from an arbitrary initial guess, but the rate of convergence is often slow. If you want to get better convergence behavior, we have to go for what we call Newton-Raphson method. Now, rate of convergence is very fast in Newton-Raphson method, provided the initial guess is selected properly. And please be aware of its next feature, that convergence is not guaranteed starting from an arbitrary guess, may not get any solution whatsoever with Newton-Raphson method. Now, let us have a look at details of what is this Newton-Raphson method, or some people simply call it as Newton's method. So, let us see how does this method look like. Once again, first let us have a look at the form of this method for a single equation, and then we would generalize it for a system of equations. So, for a single non-linear equation f x is equal to 0, we will first have a look at how does this scheme look like. Now, this f x is a function, so it can be expanded in Taylor series. Around, suppose we have got an iterate called xk. So, around xk, this expand it. So, f of xk plus x minus xk del f over del x let us put df by dx, we are dealing with a single variable at xk plus x minus xk whole square divided by 2 d2f over dx square at xk plus so on. So, let us retain only the first term, that is retain the terms containing the first derivative only, ignore the higher order derivatives. So, retain only first two terms and then what we will get, f of x, can approximate it as f of xk plus x minus xk times df by dx at xk. Now, we are looking for a new iterate or an improved solution. So, if xk plus 1 were the solution of fx is equal to 0, then of course f of xk plus 1 is also equal to 0. So, let us substitute that in equation 2. So, we get on the left hand side we will get 0 f of xk plus x of k plus 1 minus xk df over dx at xk. Now, let us call this xk plus 1 minus xk by a shorter symbol delta xk. So, delta xk is equal to minus f xk divided by df by dx at xk. So, now we have got a way to compute the corrections. If we add delta xk to xk, we get an improved solution. So, that is what gives us our iterative process for a single equation. Now, this process can also be generalized for a system of equations. The only thing is that for the case of a system of equations, we will have to work with what we call a Jacobian matrix. We will have a set of equations which have to be differentiated with respect to different terms to obtain our del xk vectors and add this del xk vector to our starting guess to get the solution. Now, let us generalize our Newton's scheme for a system of equations. So, this is Newton's method for a nonlinear system which we can write as f x is equal to 0. Now, let us focus on the ith equation, okay, and in that case how do we find out the Taylor series expansion? So, consider ith function, that is your f I of x. So, now this f I can be thought of as a function of many variables x1, x2 and so on, where x1, x2 they are components of vector x. So, for this we have got Taylor series expansion around xk okay. Now, let us write that. So, f I x of k plus delta x k. Now delta x k represents a small increment in x k vector. So this can be expressed as the value of this function f I at point x k plus sigma j is equal to 1 to n, where n is our number of equations, del f I over del x j times delta x j. And this derivative is evaluated at point x k plus our higher order terms. So we will neglect the higher order terms, and let's suppose that x k plus delta x k represents this solution of, let us call it our equation as 1. So then what we will have, f I at x k plus delta x k, this would be 0. So right hand side, left hand side is 0, and the right hand side we have got f I at x k plus sigma j is equal to 1 to n. Let us introduce a new term called j I j delta x j. Okay. So we can rewrite this equation or rearrange it as j I j delta x j is equal to f I at x k where this j is popularly referred to as what we call Jacobian matrix. Jacobian matrix j I j, this is given by, or this is defined as del of f I over del x j. So now this equation 3 gives us our Newton's algorithm for a solution of nonlinear equations. So we can formalize that algorithm. So solution algorithm is, let us say starting guess with x0 vector, then we would say iterate in iteration process. What do we do? The first thing is compute for k is equal to 1, 2 and so on till we would achieve the convergence. So first we need to compute vector f let's call it f I at x k compute Jacobian matrix j I j at this point x k, and once we have got it, solve linear equation. Just now put our matrix notation form here, j delta xk is equal to minus vector f of xk. So, once we solve this linear equation, we will get our correction vector fk, update this solution vector. So, a new or improved iterate xk plus 1, that is xk plus delta xk, and check for convergence. So, if converged, break the process, break the iteration process, else continue. So, this is our body of the iteration process, and iteration process. So, in fact, what we have just written on the screen, that is also the pseudocode for this Newton-Raphson algorithm. And what I would like you to do is translate it into a code in your favorite programming language and use it to solve sample set of nonlinear equations. So, exercise 1, they are all coding exercises or programming assignments. Programming assignments. Write a program for solution of a single equation using a sequential iteration, and B Newton-Raphson method. So, once you are comfortable with this program, you have tested it for your own example problem, then you can extend it and you can use that confidence to write a code for a system of equations. So, write a program for solution of a nonlinear system based on a sequential iteration, the same set basically, sequential iteration, and B Newton-Raphson method. For the linear solver which is required as a part of these schemes, I would recommend that you search the web, get a black box solver, use that as a part of a program. So, to conclude our discussions on Newton-Raphson method, we have already noted that rate of convergence of this method is very fast. It says the rate of convergence is quadratic if our initial guess is close to the final solution, but remember, convergence is not guaranteed is starting from an arbitrary guess. To ameliorate this situation, there are various versions of various algorithms have been proposed in literature. This one popular scheme which you can find in the numerical recipes book is called globally convergent Newton-Raphson method, which is based on line searches and backtracking in conjunction with the Newton-Raphson iterations which we have just seen. So, if you are interested in this algorithm, please have a look at the book of Press et al. Now, please remember that most of these methods we have already seen in the case of Newton-Raphson method, they require solution of a linear system at each iteration. So, we need an efficient linear equation solver irrespective of the nature of a problem, whether a problem is linear or non-linear. If it is non-linear, we have to use a linear solver in conjunction with Newton-Raphson or sequential iteration scheme. If a problem were linear, of course, we need a linear solver to solve our problem. And please remember that our choice of the linear solver must account for the basic nature of the discrete algebraic system, that is to say our system had a sparse pattern irrespective of the method which we use. We have already seen the form of algebraic system with finite difference discretization. With finite volume and finite element, the sparsity pattern is fairly similar. The system is never full, it is very, very sparse. Okay. So, this algorithm which we choose for the solution of this system must account for this sparsity. It should not require more storage than what is absolutely needed for our sparse system. There is yet another thing which we can take care of while choosing a particular numerical algorithm for the solution of a linear system, which is based on whether a matrix is general or it is symmetric. If it is symmetric, and in addition to that, if it is positive definite, there are a set of algorithms available in literature which work much more efficiently than an algorithm for a general linear system. Few of such algorithms we are going to discuss in detail in the next lecture. So, next two lectures will focus on the linear equation solvers, specifically for sparse linear systems which arise in finite difference, finite volume or finite element analysis of CFD problems. So, a few references for what we discussed today. This Press et al.'s book, Press numerical recipes, it is written in there are 3-4 versions available. You have got numerical recipes in Fortran, numerical recipes in C, numerical recipes in C++, and numerical recipes in Fortran 90. So, depending on your choice of your language, you can pick up one of these books, or from your library you can get any book. The basic algorithms are the same, only the coding part would differ a little bit. This is published by Cambridge University Press. Few algorithms can also be found in this book on computational fluid dynamics by Ferziger and Parikh. So, this way we would stop with this lecture. In the next lecture we will see few useful algorithms for solution of linear problems.